Okay. Well, we'll try to fix that.
Hopefully.
But, don't be afraid to ask questions. That's how you learn.
That's another advantage taking the practice test, and it'll do two things. Number one, it'll direct you to where you need possibly a little more study. Plus, as your scores come up, it will increase your confidence.
Okay, our old friend Benjamin Franklin was quite a character, and most people think he discovered electricity. Well, he didn't. But one of the things he did, good or bad, because they didn't know any better, he arbitrarily defined a bunch of things like potential, current, conductor, positive, negative, insulators, and charges, even though they didn't really understand what an atom was and how charges move and all those kind of things. And his arbitrary decision that electric current flowed from positive to negative, and we still follow that. That's called conventional current flow. It's not the way it really works, but it's just been so long, and in most cases, it doesn't make any difference which way, whether you use conventional current flow or electron flow, which also isn't exactly correct. We call it direct current if it's always flowing in one direction, whether you call it conventional or not, if like from a battery. We call it alternating current when it actually changes direction, which is what you get out of your wall socket at your house. It's 120 volt alternating current, and it goes from positive to negative and back 60 times a second. So some of the terms you need to get familiar with that we'll talk about is one of them is charge. And it's the amount of elementary charges at a particular point. And we measure it in what we call coulombs, named after one of those scientists named Coulomb. We use the capital C to represent coulombs, and we use capital Q to represent charge. We also use those symbols for other things, so it can get confusing. An elementary charge is the charge that's on a single electron or proton. They have equal and opposite charges. So an atom will have some number of protons, say 14. It will also have 14 electrons, and they balance each other, so it's a neutral atom. It may also have some neutrons, which are neutral. They have no charge, and all they do is add to the molecular weight, so they have no effect in the charge. Just to give you an idea, a coulomb is 6.24 times 10 to the 18th elementary charges. That's a very big number. And we'll talk about scientific notation in a little bit if you're not familiar with it.
We just covered this literally 2 days ago in math. Woo!
Good.
So we're very excited.
Okay, we define current as the movement of charge, and we measure that in amperes. Again, another French scientist, I think it was Charles Ampere. We use A to represent amperes or amps. And one of the exam questions will be, what is a unit of current flow? It's an ampere. 1 ampere is defined as 1 coulomb per second of flow. So 6.24 times 10 to the 18th effective electrons move to create 1 ampere per second. We also have voltage, which is the potential difference between charges. and it creates a force. And we call it electromotive force. That's why we use E to represent it in electronics. They use different symbol in physics just to confuse us. We measured in volts, again, named after, I forgot his first name, Volta, and we use the V to represent it. And that force is the energy per unit of charge. And it's equal to, and I showed epsilon there as how physicists represent the electromotive force. It's 1 joule coulomb. And the joule is 1 watt second, I believe. You don't have to know joule. It's not a bad thing to know, but it's not on the exam. Okay, we also will deal with resistance, which is the opposition to current flow. So voltage, potential, force is what causes current to flow, charges to move. Resistance is opposing that and tries to prevent current from flowing. And we define it as the energy per unit of charge, per unit of current. Okay, in other words, 1 volt per ampere is 1 ohm. And we use the formula resistance is equal to E divided by I, where E is your electromotive potential or voltage, and I is your current in amperes. If it's a direct current, like we said, it flows in one direction. For instance, a battery is always direct current. It goes from positive to negative in conventional current. Alternating current reverses direction at some frequency. So essentially all radio waves are alternating current. Your household current is doing it 60 times a second. And by reversing direction, it means it has to cross zero. In other words, it has to actually go from positive to negative and then back. We'll talk about conductors, semiconductors, and insulators. Conductors are materials which allow current flow. Usually it's a metal or semi-metal. We use silver is actually the best conductor. Copper is like second, gold third, aluminum fourth, and then you get iron and things like that, which are conductors, but not as good. All conductors will have atoms that have 1 to 3 valence electrons. And we'll talk a little bit more about that if you don't know what a valence electron is or what's inside an atom. And atoms have different numbers of electrons associated with the protons. And each level is a different amount of energy for that band. And the outer band of the atom, the outer shell, is what we call the valence shell. Regardless of how many shells are in the atom, how big it is, the outside is always called the valence. And that energy, amount of energy it takes, and I can't explain why electrons sort of like orbit and why they're not collapsing down since they attract to the protons, but there's some mechanism in there due to the amount of energy they have that separates them from the nucleus. And those are discrete energy bands within the atom. In the case of a conductor, there's also another energy level called the conductance band. In a conductor, the valence band and the conduction band sort of overlap. So you wind up with free electrons that are free to move with no or little excess energy in order to make them move. When you get down to a semiconductor, the valence and the conduction band are separated slightly. So it takes some energy in order to move an electron to that conduction energy band. And that energy comes from an outside force like heat, could be photons hitting it. It could be the electromotive force of a voltage potential, which is supplying energy to it with that force to actually move it. And part of that band, called a band gap, is what you'll see when we talk about semiconductors, of why it takes a certain amount of voltage for it to conduct, like in a diode or a transistor. And we have insulators, which have a very wide band gap. The difference between the energy level for the valence shell or energy band and the conduction band is very wide. So it takes a tremendous amount of energy, many, like 4 electron volts or more, to move it. So you get no current flow until you get actually enough energy to make those electrons move, and then it's usually called arcing over on the insulator. Some of the examples are insulators: glass. I didn't list quartz, which is a good one. Ceramics, plastics, rubber, all those kind of materials are usually very good insulators. And they also have 5 to 8 electrons in the valence band. And I missed the semiconductors, all seem to have 4, which is kind of in the middle. This was sent to me by a student in the previous class as an example of how these things relate with voltage and current and resistance, where the voltage is trying to force amp through some conductor and the ohm is resisting him. So voltage, we mentioned it's electromotive force or electric potential. We use E to represent it. And that's what creates current flow, or can create current flow. We have a typical circuit here with a battery and a resistor of some sort. And we're going to have some current I flowing through that circuit, depending upon the ratio of the battery voltage to the resistance. A lot of people like to use a water analogy, where the height of the water represents the pressure. So that water pressure is equivalent to voltage. And if we have, in the first drawing there, it's blocked off, so we have no current. Basically, you got an insulator or a switch there. So there's no current flow, but you do have pressure. If we open that valve, it's equivalent to lowering the resistance or opposition. So we still have the same voltage, and now we have current flow. And just like a battery in the real world, as that tank lowered because of the water flowing out, the voltage is going to drop, or the pressure is going to drop. Same thing would happen in a battery. As you use up the energy in the battery, the voltage decreases because you've got less charge difference in it. So that voltage or that potential difference, okay, with you've got positive charges on one terminal of the battery or source and negative charges on the other, creates an electric field between them. We call that an electrostatic field. And there's really 2 kinds, and we'll talk about electromagnetic fields a little bit later. And electromagnetic waves are composed of both electrostatic and electromagnetic fields. The force that's generated What?
Robert wants in.
Oh, Mr. Hunter. Did I start recording?
Yes.
Believe me, isn't it?
Thank you.
Is Mr. Hunter there?
Yes, good morning. Sorry, I just woke up here. It's early in the morning here. Good morning, everybody.
Okay,
Sorry I'm late.
all right. That electrostatic field or force, okay, is what can cause electrons that we talked about to be moved because they supply energy to them to the conduction band and actually cause them to move. And we call those free electrons. Now, there's a lot more free electrons in a conductor like a metal because of the overlap between the valence and the conduction band. And you get more activity supplying energy like heat. That energy that is in the electron when it's free, because it's higher energy than when it's back in its valence band, has to go somewhere when that electron recombines with a what we call a hole or a positive ion, which means an atom that's missing its electron. And when it goes back to the valence energy level, that difference in energy is released in the form of photons. And you think of photons as light, but it's really a say radio wave of a different frequency. The amount of energy that's released determines the frequency of the photon. So if it's low energy, you're going to see it down in the infrared range, which would be heat. If it's very high energy, it's going to be way up in the ultraviolet. One of the things that takes advantage of that when we talk about light emitting diodes, that's one of the ways they generate the color by manipulating material where the band gaps are different. So the amount of energy released determines the frequency of the light. So that's how they can get some of the colors with LEDs. Some of the other colors like white and blue take other things. But that low energy, like you see in a conductor, because the difference between the valence and the conduction band is very small. It's a small amount of energy. So when it recombines, that energy basically generates heat, which is why when you have current flowing through a conductor, it generates a small amount of heat. When it's flowing through a resistive device, which has a much bigger energy band, it's going to generate more heat. If you got enough current, it starts generating more light that you start to see as things start to glow. Okay. I was going to attempt, and we'll see how good I am at doing a physics demo. Can I pause this one?
Yes. Well, no, that's pause to share.
Where is it? Yeah.
Well, it's got a pause share there, but we want the people on the other end to be able to see the demo, right?
Right. I need to turn the camera on. Well, I'll just stop sharing.
Oh.
And let's see. Oh, that's the webcam. Okay. So we got Jack. All right. Let's try to demonstrate electromotive force. You care to hold the balloon? Sure. Since I couldn't find a glass rod.
Well, they should be able to see, not we're seeing, right?
Uh, yeah, you're kind of dark.
You can see the balloon. That's my question. Are they seeing what we're seeing? 'Cause-
Nah, we're only seeing your arm, man.
Yeah,
Might need to step to your right there.
well, just that whole.
There you go.
There's the balloon. There's a face.
You can temporarily turn the background off and it
Yeah, I can
will
come back on.
show everything.
Yeah, I'm looking how to turn it off.
I'm seeing a yellow balloon.
Oh, there we go.
There we go.
Oh.
Okay,
No.
so I'm going to charge up my PVC rod here. What that's doing is the friction is actually displacing electrons.
So if I can get the camera so I can see what you're doing. I can't see you.
There you go.
They don't need to see me rubbing a rod. So I'm mechanically stripping electrons either onto the rod or the piece of wool. I'm not sure which. It doesn't really matter. What?
You lined us.
Huh?
Too much humidity in the air in the area.
Maybe.
Too much.
It works at home, moving it a little bit, but not really enough for you to see.
Oh, there it goes.
That's Dan blowing it.
Ah, not a very good effect. Must be damp in here.
I just think it's one of those myths like Benjamin Franklin. There you can see it, it's here.
Yeah.
Yeah, that movement is your rock.
Yeah. Yeah, because you're not touching the bottom.
I might have to invest in a glass rod, but I didn't want to spend the money. Maybe the.
Try that one, sit.
Both. Maybe that works better. I know I can make them roll around on the tables.
The sun and the.
Mm-hmm. Oh, there you go.
Right down there.
Yeah.
You're right on the other side of them because you're pushing it away.
Yeah, because the charge
They come over. This
went
side.
to that. Now they're opposing, but where it was subtracting.
Come on this side, go that way for that. They're kind of blocking the ball. Yeah, you see it there.
So is that just a little ball of foil?
It's a piece of, it's a polystyrene foam ball that I just wrapped with tinfoil, with aluminum foil.
We have a new party trick.
And you notice when it makes contact,
Yeah.
the electrons transfer, and now it's,
Wow, look at that.
Mm-hmm.
well, anyway, you can see that there's actually a force there due to that difference in charge. And one of the things that's happening, which I only learned about fairly recently, is that when you think of an atom, we think of these round little spheres and got electrons running around in them and everything's nice and orderly. And it turns out that because some of the more modern models for atoms they talk about an electron cloud because they still don't know how this stuff works. So you got all these electrons running around in all different directions at different energy levels, and they're free to move. So when you move a charge, either a positive or a negative charge close to an atom, what happens, say it was a positive charge, the electrons tend to change their orbit, let's say, and that atom is no longer round, and they tend to move towards the positive charge. So you wind up with, now you have what's called a dipole, where that atom, one side of it is plus and one side of it is minus, because they're not equally balanced and counteracting one another. Likewise, if it was the opposite, if it was negative, then the electrons would move to the other side of it. That kind of happened in that demo as part of that. Okay. Let's go back. See if we can find where we were.
I just have a quick question about that demo
Okay.
in practical terms. I don't even know how to ask the question, so bear with me. Total layman here. So when you did you charge the PVC pole or did you strip it?
I don't know.
Let's say you charged it, right? Let's say that's what happened, because I'm assuming that's why it would have, if it's more charged, it would have created that opposing force, right? Because it's like matter that's pushing it away now.
Right.
But then what happens? Does it start to dissipate into the air, or what is happening? Because it doesn't remain that way, correct?
Well, it would if we were in a vacuum, but because there's humidity, which the water is somewhat a conductor, it's going to dissipate the charge. Plus, some of it would migrate back through me to ground.
Because you're a conductor.
Right. Especially
Okay.
if I was standing on a better grounded surface, like be barefoot instead of having rubber shoes on. Yeah, I guess it's a lot more humid in here. That's why I was sweating when I got here, I guess, than it is at home, because it worked a lot better at home. Let's see. Where were we? There we go. Whoop. Is that because it's already open? Oh. All right. Let's try it this way.
So while you're finding that spot, but we were wondering, is it the same as like in the olden days when they had to like restart cars and they had to like crank them? Is that basically what they were doing? Is they were creating a
Charge.
was it something?
No, there they were just mechanically turning the engine over, and part of that engine mechanism had a ignition coil, which there was a switch that would cause current to flow through the coil and generate a spark in the spark plug. So indirectly, they were causing a current to flow, but fairly indirect.
On the starter, like today's starters, we put a charge, run a current through to build a capacitance.
Well, no, in the
So
starter, it's electromagnetic field. We haven't got there yet,
oh, sorry.
Sorry.
but that's a good question. Now I got to figure out how to. All right.
A similar type of a principle, like with like charges and unlike charges, is if you play around with a Van de Graaff generator,
Right.
because you have the belt is an insulator and it's running through a series of a copper comb that picks
Right.
up the negative charge, makes the sphere a negative charge, and transfers that discharge to a positive source. So yeah, you can do the same experiment with the
Right.
foam ball with the Van de Graaff generator.
I
Is
might
that
have
something
to.
that they would use on a farm or in?
No, it was actually used as a like before our times as as a form of a rough form of a capacitor.
That's
Or
cool.
like if you watch those old movies like Frankenstein,
Oh, yes.
they would have a form of they would have that Van de Graaff like with a. So I'm big into this stuff here.
That's cool.
That
The atom.
Walter Lewin's site has some lectures where he does a number of things with a really big Van de Graaff generator. He stands on it and touches it and has his hair stand straight up and all that kind of stuff. And that was one of the things when I was playing with this at home, I could actually raise the hairs on my arm with that rod, and you could actually feel the force as you moved it close. So it must be a lot more humid in here. Okay. Can everybody see this slide?
That copper
Yes,
ore.
sir.
Okay. I just picked copper because that's one of the things we'll deal with the most. It's the primary conductor that we use. It's not as good as silver, but silver is quite expensive, although copper is getting there. Copper has four electron shells, we call them, with one of the older atom models. And you notice that the outer or the valence shell only has one electron in it. And because it's one of the metals where the conduction band and the valence band pretty much overlap, a lot of those electrons in the valence shell are essentially because of temperature, where it's getting the energy, are free to move around and go from one atom to another if it's missing an electron. And these shells, and I don't understand the mechanism, but they're always, the K shell always has one or two electrons and protons. The I shell always has up to 8. The M shell has 18. The and I don't know what they call this when it's not the valence shell. It will have a fixed number. I believe it's 8. And
In chemistry, we call that the valence electron.
right. And that's why they call it the valence shell, and that's the valence energy band. It's also, if you, in chemistry, you talk about covalent bonds. where with two atoms, they can share an electron in this valence shell. And that's how crystals are attached to one another or other chemical compounds. This just shows for metals where you have the energy levels overlapping. And this dotted line in here is called the Fermi level, which Enrico Fermi, one of those, I think he was Italian physicist, came up with this energy level where the probability of an electron being on one side or the other is 50% at that energy level. So, and you can see for an insulator, the band gap is very much larger. So that's why it takes a lot more energy to get an electron to move if it's an insulator or a very, very high resistance material. So let's do a question. What is the electrical term for the force that causes electron flow?
Voltage.
Okay. You're right. Electromotive force or potential, we call it voltage and use E. The other answers there, ampere hours, would be a unit of charge, and that would be equal to 3,600 coulombs. Because a coulomb or an ampere is 1 coulomb per second, so there's 3,600 seconds in an hour. Capacitance, which we haven't talked about yet, is the ability to store energy in an electric field. And we were actually storing some energy, be hard to measure when we did the demo. And inductance is the ability to store energy in a magnetic field, which we'll talk about later. Current, okay. That's the flow of electrons, or actually charges, moving from one atom to another in a circuit. It turns out that even though they called it electron flow, which is opposite to conventional current, electrons physically move at 0.01 millimeters per second. That's even hard to see. So they tend to move around, but it's the force, the electrostatic force, that's causing the charges to migrate in one direction or another, regardless of where the electrons are going from atom to atom, because they'll go from whichever positive ion or atom has a positive charge on it. So it may move in this direction or it may move in that direction. The aggregate with the charge is the charges tend to move in one direction or the other, regardless of where the electrons are going. So that's why electrons don't really, I mean, it would take forever for an electron to go, from one end of a 100-foot piece of wire to the other at the speed they move. But the charges move at the speed of light. In one of the demos, remember in physics class, when they talked about that, is the professor took a hollow tube, filled it with ping pong balls, and if you tapped on the ping pong ball at one end, the one on the other end would instantly fly out, because you transferred that energy at not quite the speed of light, but instantaneously. So that's the way what we call holes move, as opposed to the electrons. Let's see, and we measure current in amperes. We talked about that. Use A. Again, that same circuit, So if we had 1 amp of current flowing, means we got 1 coulomb, or that 6.24 times 10 to the 18th elementary charges moving per second. The water analogy again, voltage is the height of the water, which is the pressure, and the size of that pipe is going to determine the amount of flow or the amount of amperage. Okay, so this sort of represents resistance. The less resistance you have, the more flow you're going to have, the less flow you're going to have, until you've got it essentially an insulator where you have virtually no flow until the pressure is high enough to actually break through. So what is the name for the flow of electrons in an electric circuit?
What's D?
Current.
Current.
Okay. Oh, let's see, is there anything? We talk about resistance, which we'll get to again here. And capacitance is the ability to store charge. And voltage was the force that causes the electron flow or the charges to actually move. Electrical current is measured in which of the following units?
Volts.
Volts.
Electrical current, remember, read the question. Current
I'm going with D. Amperes.
okay. Yeah, practice using the phonetic alphabet when you answer these. Alpha, Baker, Charlie, Delta. Because you'll need to learn it later on. So it's amperes,
Delta.
coulombs per second, right? Resistance is the opposition to current flow, and it's all types of current. It's frequency independent, which means it's the same whether it's a direct current circuit or an alternating current circuit. Now, when we talk about a little bit later, we'll talk about capacitors and inductors, and they're frequency dependent. They oppose current flow at certain frequencies. So where resistance is always the same amount of resistance, regardless of the frequency of the current. We measure it in ohms. Sometimes you'll see the Greek letter omega, which is that little horseshoe to represent ohms. Or else we spell it out as a capital OHMS. It's a proper name, named after, I forgot his first name, but his last name was Ohm. And he's responsible for Ohm's law, which we'll get to here in a minute. Again, the water analogy, just a different version of what you've seen, where the constriction is the resistor or resistance, which is controlling or limiting the amount of current flow depending on the pressure or the height of the water in the tank. In simple terms, the current flow is going to be proportional to the height of that water. Turns out in real life, there's other factors and it's not exactly true. But for our purpose, we'll assume that's true. What are the units of electrical resistance?
Ohms.
Would that be Charlie?
Charlie.
Charlie.
They put Siemens in there, which you'll never get to in the technician exam. It shows up on the extra. It's a unit of admittance. Mohs is ohm spelled backwards, which is a real thing, and it's the units of conductance, which is the reciprocal of resistance. So it's 1 over resistance. And we know coulombs are units of charge. So what type of current flow is opposed by resistance?
Delta.
It's one of those, all these choices are correct, which happens occasionally. Okay, we call it direct current because the polarity or the current always goes in one direction, positive to negative. So if it's coming from a battery, for instance, it's always positive to negative. If it was coming from an alternator, like in your car, it's actually alternating current that gets rectified into a DC current. Alternating current, your typical household is 120 volts AC in the United States. It's like 220 in a lot of Europe. I know in Britain. We're 60 cycles. I think Europe is mostly 50 cycles. Military is, what frequency do they use? It's not world on, like on aircraft.
Aircraft carrier, well,
Aircraft themselves, but
well, it depends on the aircraft. So those are 400.
400?
3 cycle,
okay.
but, yeah, what I do know is they made a little pigtail where you plug it in the aircraft outlet power and had a regular household outlet on the end, and plug in a boom box there and all work for a few minutes.
So the main thing is that alternating current alternates between positive and negative directions. And it really must cross zero. If it's increasing and decreasing like a sine wave, but it never crosses zero, we would call that pulsing DC. It's not alternating direction. It's increasing and decreasing, but it's not changing direction. There's an example of and most of the time we're going to be dealing with what we call a sine wave, which if you look at a circle, which is how these get derived, and you rotate that circle in steps, let's say we're doing 30-degree increments all around here. So for every one of those 30 degrees, we look at what would be the sine of that angle or the height from the base up to this point, and we plot it with the degree scale. It's going to plot out a perfect sine wave. That's how they're defined. And the mathematical symbol is, if you use your calculator, there will be a sine function. They used to have to do that with a set of tables, sine tables. You'd have to do a lookup. You'll notice in here they talk about radians. You won't be using radians, unfortunately. When I took electrical engineering, all we did was radians. And they use omega to represent 2 pi times the frequency radians per second. If you notice the circle, the circumference is 2 pi times the radius. which is where radians came from. So if you say the radius of a circle is 1 radian, or is a radian, there are 2 pi of those radii in the circumference of that circle, regardless of the size of the circle. So that's why one of the reasons why they mathematically use that, and it's also shorter to say omega t or omega L, as opposed to writing out 2 pi f. So which of the following describes alternating current?
Charlie.
Charlie sounds good. Now, A and B are just varying DC because it never goes in the opposite direction. And obviously, all of these answers are correct, can't be correct, since 2 of them are wrong. Okay. When we talk about alternating current or radio or light, okay, they have frequency. And it's the number of times per second that they change direction. So your 60 cycle house current is changing direction 60 times a second. Now, it's not on the exam, but there's also the period, which is the length of time it takes for that waveform to complete one cycle. Okay. And that's the reciprocal of the frequency, call that the period. We'll see time period show up a little bit when we talk about RC circuits with charge and discharge, which is based on the time constants. So what describes the number of times per second that an alternating current makes a complete cycle?
Wavelength.
Delta.
And let's see, your pulse rate is how many heartbeats per second? Speed is the distance or revolutions per second, and wavelength is the distance, and we'll talk about wavelength later, the distance the wave travels in one cycle, which is similar to the period, but it's actually the distance. So you have to factor in the speed of light. And I don't think I mentioned this one. I should have. What is the unit of frequency?
I'm gonna go with alpha.
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 Yeah.
Named after Mr. Hertz. And because it's a proper name, we use a capital HZ to represent it. Henry will show up a little later as a unit of inductance, named after Henry. And units of capacitance are named after Farad, Michael Faraday. And then Tesla is in there for units of magnetic flux. We call those Teslas. Okay. We talked about conductors, and these little things show in the free state where there's no voltage or potential, you still see these free electrons running around, and they can move from one atom to another. So if an atom loses an electron, it becomes a positive ion because it's no longer balanced. So it's free, and we call those holes because there's a missing spot. There's a missing electron. So an electron from a free electron that came from another atom can fill that hole. When we apply a force or a voltage across that conductor, that electrostatic field, that tends to direct those charges that are moving to fill in the holes, the electrons, in one direction. And that's where you get the current flow of the charges per second, or coulombs per second. And there's our copper again, which we talked about with the one valence electron, which is very easy to move, which is why it's a good conductor. This is just another one showing the conduction and valence bands and the band gap. We'll talk about that probably more when we talk about semiconductors, because that's where it really becomes a lot more important to understand it. Okay, so conductors are typically metals. They could be a semi-metal, or some liquids like mercury is one, which is a fairly good conductor. We use it in thermostats, used to use it, things like that. There's a thing called resistivity, which you'll find, you can look up, and it specifies the amount of resistance per meter, I think it is. And this is just showing the relative amounts of resistivity for silver, copper, gold, aluminum, mercury. And you notice that there isn't a lot of difference between silver and copper, which is why we tend to use copper, and it's a whole lot cheaper. You would think gold is much better than it is. We use gold a lot to plate surface of conductors and things like that because it doesn't oxidize, it doesn't tarnish. Whereas
What
silver,
metal do they use in for space? What's the preferred metal?
in space,
Yes.
don't know that there's any difference. In the spacecraft, NASA spacecraft, back in my day, we used copper wire. I know at Oak Ridge, back in the days of developing the atomic bomb, some of that research there, they used a lot of silver wire because they had kind of an unlimited budget and wanted. But typically, we use copper for most things. You'll see gold-plated or nickel-plated conductor surfaces, sometimes silver on conductors. Problem is it tarnishes. So if it's not an airtight seal, it's gonna become a bad connection over a period of time.
Just a tiny bit of trivia, I used to work in circuit plating. Copper and gold are incompatible. So if you need to put gold on the surface, there has to be a layer of nickel between it. And nickel isolates the gold and the copper so that they won't deteriorate each other.
And sometimes the cheaper ones, they just nickel plate them.
Yeah, they just nickel plate a lot of it, but the stuff that I worked on, all the company that I worked for specialized in high frequency applications. So most everything was copper and then nickel and then gold. And rarely there would be like 90-10 on top of the copper instead of gold. It's going to be soldering stuff.
So why are metals generally good conductors of electricity?
I have a question real quick.
Okay.
So you know how it said in the chart like 1.59 for silver. What does that specific number mean? Is that like how much it costs, or is that like the weight of it, or
It's the amount of resistance per meter, I believe. In other words, it's ohms. It's like ohm meters. It's a weird thing, but essentially it's the relative amount of resistance per unit. So you see that silver has less resistance than copper.
Mhm.
I mean, you get up to things like actually mercury is a lot more resistive than I would have thought. Because you see it's 10 to the minus 7th instead of 10 to the minus 8th. So
Right.
that's 10 times more than the others just on the exponent.
Hmm.
So conductors have many free electrons because they're in that overlapping valence and conduction band. There are no free protons. It takes a accelerator to get a proton out of an atom. Not all metals have high density. Aluminum, for instance, is pretty light. Some of the other metals like lithium and things like that are very light, semi-metals. So insulators, okay, sometimes we need something that doesn't conduct because otherwise everything would be shorted out. We call them insulators. In some cases, we call these dielectrics, which is, I think, a Greek word for meaning it's non-electric. Because they have a very high resistance or opposition to current flow. And plastics and glass are what you see most of the time. I'm not sure where you see quartz as an insulator. It's a good one, but mostly you're going to see plastics or glass or ceramic or silicon itself. Intrinsic silicon, which is pure silicon, is an insulator. And we'll talk about that when we talk about how you make a diode or a transistor.
It is sometimes used to insulate underneath some
Yeah,
resistors and stuff.
we use a lot of Mylar on the spacecraft. Let's see. So a comparison of conductors and insulators, as I mentioned before, the conductors have 1 to 3 valence electrons. The better ones have 1, like copper and silver. Insulators have almost a full shell, which is up to 8. Conductors have a low electronegativity and insulators a high electronegativity, and this is not my chart, and that's a very confusing term.
Yeah.
So you don't have to know that one. And the examples are, silver, copper, gold are good conductors, basically metals, and insulators are mica and glass, plastic, ceramics. So which of the following is a good electrical insulator?
Thing.
Bravo.
Okay. Yeah, the other 3 are all conductors. So we learned that current is measured in amps and it's 1 coulomb per second, which is a whole lot of charges per second moving. Direct current flows in one direction, alternating current changes direction per cycle or per hertz. We used to call those cycles per second, and it wasn't all that long ago it got renamed to hertz. The electromotive force or volt we measure in voltage is the force that actually imparts energy to those free electrons. We measure frequency in hertz, capitalized because it's a proper name. It's equivalent to the number of cycles of the waveform per second. We measure resistance in ohms, and it's the opposition to current flow. Conductors have many free electrons. That's a key one because that's what they ask on the exam. And insulators are basically non-metals. You really only need to know like glass and quartz or good insulators. Any questions so far?